Okay, so my talk will be in English. Okay, and its main purpose is to connect the simplest notion of proof theory, okay, the simplest notion of proof to nuts. Okay, so in general, people interested in proof theory, they like to look at big systems. Okay, so typical example is set theory or other generous systems. But here we'll just do the inverse. So we'll look at the simplest possible notion of logic. Okay, and the idea is that it should be so simple that maybe we can use new tools, and essentially these new tools come from 2 or 3 category theory, okay? And using them, connect this very simple notion of proof to knots, okay, topology of knots. And the purpose of all this is to have some kind of better understanding of where logic comes from. Okay, so there are no apparent connection to physics. On the other hand, there is some kind of jealousy. Okay, like logicians in a way should be very jealous of physicists because they have a lot of concepts, and from the concepts they deduce well, some properties like preservation of energies and so on. So the question is, can we do a similar thing in logic and deduce, for instance, a proof system from the basic symmetries? Okay, so what are the symmetries of logic? Well, a typical symmetry is the fact that in a discourse of reason, okay, this is axiom 1, if you like, there is a symmetry between the guy who tries to prove and the guy who tries to refute. Because any time the refutator may become the guy who tries to prove that he's right refuting. Okay? So this symmetry is very important, and if you like, the question is whether this kind of symmetry comes out in current algebra. Okay? So in order to go from proofs to nuts, it's good to look a bit at representation theory of quantum groups, because there is a beautiful connection between this representation theory and nuts. Okay, so we see how to do that, but maybe it's good. It's good to start very like to explain where I come from, and essentially is this line of works, and so it's the idea that a logical proof is a mathematical object. Okay. But if you say that, then the question is, what kind of mathematical object is it? And in a way, the whole field has been striving, you know, generation after generation, to connect to like mainstream mathematics. Okay? And in a way, you can think of what I'm doing here as another step in this sequence of attempts. And so if you look at the typical proof, it's, you see, like this, okay? So this is a proof of a formula here. Sorry, this is my Mac. So this formula here, okay? And the proof is built by a sequence of logical rules. And it's kind of perplexing to think that, well, it looks a bit like, you know, a musical score, okay? So you need to be an expert to read that off. At the same time, where are the flows, okay? So logic is supposed to speak about us, I mean, the way we interact, okay? And we don't see much of the interaction here, okay? So the idea is, well, maybe can we build some kind of, you know, notation for proofs that would look a bit like this. We see some flow. And clearly, these kind of diagrams we will see, they are naturally expressed in a monoidal category. So this is so-called string diagram. So we'll try and connect logic to these monoidal categories. We see that we need a bit more, but this is the starting point. And in fact, so I will work on a very simple, kernel of logic. It's so simple that apparently it's not interesting at all. Okay, it's just a logic with a tensor, and the tensor is like a conjunction and a negation, and that's it. Okay, so it's in a way everywhere. If you in any logical system, you would have this, and what happens is this very little thing. Okay, this very little logic happens to be very well connected to so-called dialogue games. Okay, so dialogue games are a way to organize logic and to see a formula as a game and a proof as a strategy trying to win the game. Okay, so it's a winning strategy in the game. And so the whole purpose of the talk is to show that in fact it's possible to merge together these game semantics, okay, so these ideas of strategies, with knots. And in fact, that the notion of strategy is already there, if you like, in the representation theory of quantum groups somewhere. Okay, so how do we do that? Well, the first thing is to start from the so-called functorial approach to proof invariance. Okay, so we want to build invariance for proofs. So how do we do that? Well, typically, we start from the notion of Cartesian closed category. Okay, so it's a Cartesian category with a notion of function space, okay, inside, and then we construct the free Cartesian closed category. So how do we construct it? Well, the objects are formulas constructed with products and implication, and then the morphisms between these formulas are proofs. Okay. And the proofs in this setting, they are called lambda terms. Okay, and so you need to have lambda terms. Well, I think I will jump a lot. Okay, so you need lambda terms and some notion of equality between them. And once you have your proofs modulo equality, they are exactly the morphisms of the free Cartesian closed category. So that's the way to build the proofs. Okay, so it's a bit like what we saw previously. It's quite syntactic. Okay, so this is the system. And there are some notion of equality between proofs like this. So these equalities are very important in logic and computer science. Okay, so, but the point is, once we have the free Cartesian closed category, okay, and we know that the morphisms there are the proofs of our logic, then every time we have a Cartesian closed category D, okay, and a functor from a category of, if you like, logical atoms here, okay, so the basic atoms of the logic. So every time we have a functor from a category C to a Cartesian closed category, we can lift this functor, and this produces a so-called semantic functor, which to every formula here, okay, associates the corresponding object in the category D. Okay, so in particular, this functor preserves Cartesian products and implications. And to every proof in this category, so remember, a proof is a map here, a morphism here. It's transported to a proof, to a morphism in this category. And the notion of equality between proofs, okay, is preserved by the functor. So every two equal proofs have the same image, okay, by the functor. So in part, yes?
Very simple question. Should I think of tensor product as the logical connected and?
Exactly, yes. Okay. So in that case, and this is known, this has been known for 40 years nearly, okay, since the mid-70s. So it's good to think of the Cartesian product of a category as a conjunction, okay? And so if we do that in this setting, then really the logic is organized, and the formulas and the proofs are organized into a Cartesian closed category. It's the free one, okay? So remember, the purpose of all this is to give some algebraic content to proof theory. So if we take, for instance, the free category with, like the free monoidal category with a monoid inside, for instance, we would get the category of simplices, okay, and then similar things. So this is really a way here to generalize what we would do for an algebraic theory, okay, with the notion of props or pros, okay, into logic, okay. So the main difference is we don't have just Cartesian products, we have implications too. Okay, that's it. But the thing is, if you look at this free Cartesian closed category, well, it's beautiful, but it's very syntactic. The way it's built is very syntactic. So we feel that, well, it's clever, but still this object is symbolic, if you like. Okay, so that's what we know in proof theory. And it happens that, in fact, there is a strong analogy with knot invariance. Okay? So in that case, instead of, it's exactly the same picture, except that instead of building the free Cartesian closed category, you construct the free ribbon category. So in this free ribbon category, the morphisms, so we will see that, are tangles. They are ribbon tangles. Okay? So the theorem is that this category of ribbon tangles is a free ribbon. So every time I have a functor from C from a category C to a ribbon category, I can lift this functor to the free ribbon category, and this functor now transports every ribbon tangle into a morphism here, and this morphism is an invariant of the ribbon tangle. Okay?
Sorry, now, what should I think of overcrossing and undercrossing as logic?
Yes, so that's the point of my talk. I will explain that it's possible to build a logic where whenever you permute hypotheses, you care about the way you did that. So you remember about this topological information about, whether you turn these formulas in that way or in that way. Okay? And in fact, these kind of principles underlines the structure of, if you like, the category of representations of these quantum groups. Okay. Know them, here. So it's a category equipped with a tensor product. And the string diagram notation, it's not just that you know them. Someone here invented them. So, okay, so this notion of and what I will say here is doesn't work just for monoidal categories, but also for bicategories. Okay, so whenever there is a monoidal category or a bicategory, there is so-called string diagram. So here is for morphisms in this monoidal category. So it's very simple. So every time you have a morphism from A, tensor B, tensor C to D, tensor E, you can draw it like this. Okay? So it's depicted as some little symbolic diagram with 3 inputs, okay? So tagged A, B, C, and 2 outputs, D and E. Okay, so now how do you build up your string diagrams? Well, composition in the category is depicted as vertical composition, okay? And tensor product is depicted as parallel composition, okay? So F tensor G is just depicted as F parallel to G, if you like. And so, for instance, F tensor identity is depicted like this, okay? Identity is just the trivial link from D to D. And now this is F tensor identity here, precomposed with identity tensor G. So clearly, when you see this picture, it's quite natural to ask yourself whether it's equal to this one, okay? And in fact, the very definition of a monoidal category ensures that this equality holds, okay? So this enables to understand what Penrose introduced, because this notation comes originally from Penrose, to understand and to kind of formalize their connection to monoidal categories. So now, once you have these string diagrams in any monoidal category, you may ask yourself, how may I interpret a knot inside such a monoidal category, and that's where ribbon categories come out, okay? So the idea is to add combinators. So first, if you want to build, interpret your knots, you need a notion of braiding, okay? So what is depicted here as a braiding, okay, this link coming above this one, algebraically, so this is the topology, but algebraically, it is a family, a natural family of isomorphisms from A tensor B to B tensor A, okay? So now, this is an isomorphism, so in particular, there is an inverse, and the inverse is depicted by the other, negative braiding. You see, this is the positive braiding and the negative braiding. And the idea is that the topology is here to say that if I compose a positive, so if I compose, so this is like gamma and gamma minus 1. So if I compose a positive braiding with a negative braiding, this should be the identity. Okay, so that justifies to draw these morphisms in this way. Okay, so a braided monoidal category is a category which has this braiding and satisfies these two coherence diagrams. This is the first one, and diagrammatically it says something like this. And there is another coherence diagram, and diagrammatically it says something like this. Okay. Well, so it's a way to kind of justify, to give some topological meaning, to these combinators. Okay. So clearly you need the combinators, but you also need these coherence diagrams. Okay. So this is for a braided category. Then it's good to add a notion of twist. So the twist is depicted like this. So you twist your ribbon, okay? So it's a whole turn that you apply to the ribbon, and it's seen as a natural transformation from the identity to itself, okay? And this natural transformation should satisfy these equations that if you apply the twist to the identity, so if you apply the twist to the unit, is the identity. And if you apply the twist to a tensor, it should be the same as applying braiding, then the twist on each link, and then the braiding again. Okay? So these are the basic principles. Yes?
Just before twist, it just corresponds to usual monoidal category, or there is more conditions there?
Sorry?
This diagram you showed, it's just usual, pentagon for monoidal category, or there is
I didn't show the pentagon for the monoidal category because it's there to organize already the string diagrams. Okay, so yes, it's already there, and before the string diagrams come, you need these pentagons to be sure that you have a good representation, of two cells or morphisms. So, but here, so it's again topological. It says that if you have two links and you twist the two links, so A tensor B, is the same as doing a braiding, okay, here, another braiding, and twisting each link independently, okay? So, so that's this diagram here, okay? So we have a braiding, we have a twist, and now what is the next and last combinators we need? We need a notion of duality. So duality here is expressed like this. So a dual pair is simply a pair of morphisms satisfying, so equipped with a map from the unit to A tensor B and the map from B tensor A to the unit. So this is depicted like this. So the unit diagrammatically means the empty, okay? So there is like no input and two outputs, A and B. And this is a map from the unit to A tensor B. And here B tensor A, sorry, is this map, epsilon, is described like this in the diagrams. And the coherence property of this unit is depicted diagrammatically like this. Okay, so a typical case of such a duality is in a category of finite dimensional vector spaces this is built, so in that case, the unit is the field. So this thing here is building the matrix, okay, the diagonal matrix. So it's the map from a scalar lambda to lambda, the diagonal matrix. And this is evaluation of the dual, I mean, you know, a form against a vector. And if you do that, you will see it's equal to the identity, and similarly here. Okay. So that's the three things you need. And a ribbon category is a balanced category, so it means braiding and twists, where every object has a left dual, and moreover, there is a connection between the twist and the duality. So the connection is this, that maybe here. Okay, so it says something like this. If you okay, so if you so here, imagine you have A star, and you evaluate it against A. Okay, so you apply here theta A star. So
Paul-André, is it possible you can use a different fiber tip, because it's almost...
I will do my best depending on the resource, but yes. That's true, it's quite hard to read. But essentially, okay, so maybe it's a bit better.
That's better.
Okay. But the basic idea is that if you want to twist the vector space of forms, okay, is the same as, well, just twisting the input. So here, yes, that's what the equality says. Okay, and these are the kind of things we really like in logic, because A star should be understood as negation of A. And so here, what this map A star tensor A into the base field, okay, is understood logically as the fact that negation of A and A implies false, okay, which is the basic principle of, you know, contradiction. And so it says, okay, if we want to twist negation of A and then apply this principle of contradiction, it's just like twisting A and applying the principle of contradiction, okay? And so, okay, this is a ribbon category. So, so for instance, one can show that this equation holds in any ribbon category. Yes?
Every object has a right line then?
Yes, it comes from the fact that you can, I mean, it's yes, automatic. Yes. So, yes. So there is this equality here, and we'll see that it's very important in logic too. So the theorem then by Schum, okay, 89, is the real, I mean, topological connection, if you like, or proper connection between this notion of ribbon category and the topology. So the free ribbon category generated by a category C, it has, so the objects are signed sequences. So that means you take words of objects of C, but each word is signed plus or minus, okay? And really you should think of plus as doing nothing and minus as putting a star, okay? So it's negation, if you like. So, and really the idea is, imagine you want to build a free ribbon category, then you have lots of tensors and negations and tensors and negations. And the point is negation commutes with the tensor. So you get a big tensor of a tower of negations, okay? But this tower of negation collapses to 0 negation or 1 negation. And so in the end, you have signed sequences. So if you can think of them as big tensor of A1 AK and epsilon, 1 epsilon k is either nothing or star. And now what are the morphisms? They are exactly frame tangles, but in the topological sense, with links. So they are labeled by some kind of crossbreeding. something which will be at the same time on the side of proof theory and on the side of topology. And this is what I will do now. Okay, so so this is a typical map in the free ribbon category, and we are back in the same. Remember the same picture that we had about the free ribbon category and so on. So, okay. So now, okay. How do we construct ribbon categories in the literature? I mean, what is the typical way? So the typical way is to start from a Hopf algebra and look at the left modules. Okay. So the left modules on the Hopf algebra. So because a Hopf algebra is a cogebra, we get a monoidal category. And because there is an antipode and we are very careful, we get a monoidal closed category. But in fact, it's monoidal closed on two sides. So there is a closure on the right, okay, which is defined with the antipode S. But there is also a closure on the left, which is defined with the inverse of the antipode here. Okay. So in order to do that, already we need that the antipode is invertible, but that's a basic, I mean, it's a pretty general property. It's not too restrictive. And now we built a monoidal closed category. In order to get a braiding, we need a special map, okay? So, a special object in H tensor H. We have these two representations, and we use the braiding, we will multiply by R, okay? That's because we have, I mean, multiply in the sense R will act on the two sides, okay? And now, so that's exactly, you see how it works. So we have R here, so typically it's a sum of SI tensor TI with some scalars here. And so when we commute V tensor W into W tensor V in the category of representations, what we do is we take this vector and we make R act on it, okay, and turn at the same time. So that's the way the braiding is defined, okay? And these equations on R here are here to ensure that really we get a braided monoidal categories. Okay, so now we have a braided monoidal categories, and well, in fact, it's a braided monoidal category. At the same time, we have, thanks to the braiding, a map from the left negation to the, or from the right negation to the left negation. Okay, because of the braiding, there is some isomorphism. The problem is that the isomorphism is not good in a sense. So why? In fact, we need a bit more than just braided Hopf algebra. We need something called a ribbon algebra, where there is a little theta which corresponds to the twist. And that's where the twist comes in the theory. And the whole point is in order to have a good connection between left and right negation, we need to be able to construct such a little thing here in the Hopf algebra, which is group-like. So the idea is that it's very important when we have like three inputs, so when we have a form on three inputs, so A tensor B tensor C, that we can, so I will show that, but we can turn the inputs, so we can take the A on the left to the right, and then the B on the left to the right, but we want that to be equal to the turning A tensor B to the right. Okay, I will show that a bit later, but this little twist is really important in this representation theory, and the point is that now, once we are there, the subcategory of finite dimensional modules, okay, is a ribbon category, and that's where people work usually. But a question is, what happens with the general category, not the subcategory, but the whole category of modules? And that's where something new happened, which is that in there, we don't have any duality anymore like we had, because when we, in the kind of duality here, okay, negation, so star is involutive. So a space is always like a module is always isomorphic to its double negation, okay, or it's bidual. But it's not true anymore if we remove that condition. And that's where it's useful to have logic. Okay, so really what we get is what I call a dialog category. So I will explain why, but essentially the reason is that just like the free ribbon category is a category of ribbon diagrams, the free dialog category is a category of dialog games and strategies. Okay, so the idea, if you like, is that the notion of, logic is already there in the typical representation theory or in the typical algebraic situation. And so, what is it? It's very stupid and simple. Yes?
Maybe it's a stupid question before you go. You want to go to infinite dimensional situations.
Yes.
And this means monoidal closeness is not there.
Sorry?
It's not monoidal closed.
It is still monoidal closed, yes. It is still monoidal closed, but I will focus on just A implies, the base field, or A star, if you like. So I will not, monoidal closed is too generous. So I will just fix a point, which is some kind of return, a base, and I will just consider A implies this thing. And it's very important for I don't mind about monoidal closed, but I think the primitive is what I'm showing now, okay? So it's about trying to get to the primitive structure. And it's connected to the notion of Frobenius algebra, what I'm showing now. So that's also a motivation. So, it's very simple. So dialog category is a category with an exponentiating object. So that means it's a special object I call bottom, okay? And there are just as many maps from A tensor B to bottom as maps from B into left negation of A, okay? And I will, and similarly, there is a right negation. But of course, formally, it's a monoidal category equipped with an object bottom and two natural bijections. That's it, okay? Yes? Yes, but everything is here. I think it's better for you, this slide. Sorry? What is important is, okay, this is just, okay, this is, all this says is that this functor here, okay, if you fix A here, okay, A tensor is a functor from C up into set. Okay, this thing is a functor, and you want to have it representable. That's it. Okay, so you say, okay, for every A, I have a natural transformation from this thing into this thing, and this thing is an object I pick. Okay, but in fact, after that, you can show that indeed it's a functor itself. Here, you can work on that with Yoneda, this kind of thing. But let's say this is the definition. So in particular, any monoidal closed category is like close on the left and close on the right is a dialog category for any object bottom you pick. Okay? But here I typically consider forms. So this says that if you like, the set of forms is naturally bijective to a set of maps from B into something. Yes? So this is, if you like, an internalization of the notion of form. Okay? Form on a vector space. Yes? It's like A star, but you see, usually we consider home space, A, B. But here I just consider A bottom, okay, fixed. Okay, so now let's axiomatize things. So the idea is to axiomatize the categories of representations of this ribbon algebra, so the Hopf algebras. So really what is fundamental in this axiomatization is this thing that when we have a form, okay, so from the maps here from A tensor B to bottom, we can transform any map here into a map here. Okay, so there is a natural transformation, and pictorially it's like this. Okay, it's this. Okay, so really you should think of F as a form, two inputs and one output, which is typically the base field. Okay, and now we want to say that we can turn a form like this, because bottom is a good bottom, we have some way to transform it into a form from B tensor A into bottom, okay? A map from B tensor A into bottom. So this is a basic ingredient that we want in our category. And the important point about this operation is that we want this diagram to commute. And what it says, this diagram, is that if we have A, B, C, if we turn with A, and then we use wheel again with B, we get a map from C, B, A. Yes? Because we started from A, B, C. Okay, and, sorry. So I will put myself in your direction, it's easier. So I had A, B, C, I turned A, then I turned B, and I get a map from C tensor A tensor B into bottom. But I could also just take AB at the same time and here apply the wheel once. So I have A, B, C, and I turn AB. Okay? And I want this to be equal. Okay? So I don't want to care about the order, I mean, how many A and B's hypotheses I turned. So diagrammatically it says something like this. I will, yeah, I can. Okay. And this thing is, is really justified by, logic. If you want to do some logic, you need that. You need that. You have like A, B, C here, and this is bottom. If you want to, if you turn, so if you turn this here and then do this, okay, so now you get A here and B here. You want that it's the same if you do it in two stages, or one in a go on the tensor product of AB. Okay, that's the basic equation. And the point is, yes, so there are, of course, alternative formulations of the same thing, so there are other ways to look at it. But, okay, so what I call a balanced dialog category is a category C, so it's a balanced, yes, so, okay, so this is the notion of cyclic dialog category. Now we can say, maybe this basic thing, I want it to come from some ribbon structure on the hypothesis, okay? So in order to do that, it's good to have a notion of braidings and twists on the inputs. And then the basic observation is that every balanced dialog category is cyclic. So how do you define this map? Well, you need to use a twist on the, so you see you're building, you start from a map from A tensor B into bottom. So the first thing you will do is braid the inputs, okay? But it's very important, and this is a bit unexpected from, for logicians, it's very important to add a little twist here. So it's very important to twist this formula here, if you like. So why? It's because we want this topological equality, if you like. We want that when we, okay, this is the thing that we had in the cyclic category. But now, if we want to mimic that with a braiding and a twist, we want this kind of topological equality here. So we want that this here, so we need to twist A and B, and this is what we are doing. So sorry, to braid A and B, but we also need to twist A. And the reason is that, imagine that I have A, B, C, okay? If I want to have this coherence property for cycles, it's very important that I add this little twist, okay? Because imagine I have A, B, C. If I do A first, and then B, so A and B get braided twice. See that the category of finite dimensional H module is ribbon. Okay? So it's not a very deep result, but it's a way to say that if we want to think about general dimensional modules or representations, and the categorical algebra of it is quite natural to go into these more logical kind of tainted systems. And so the the point then is once we understood what is this notion of balanced dialog category, then we can prove again this kind of generic. I mean, we can show that the free dialog category is in fact a category of proofs, but if you like, topologically minded proofs. So they remember how we manipulate the hypothesis. Okay. And the theorem is this one. I mean, this is the main theorem of the talk, is that if I start from a category C, okay, so any category, I can add a little point, a little object bottom to the category, okay? And this object bottom will mean the falsity, if you like, okay? Now, I can, now once I have this functor here, I can, because this, every ribbon category clearly has this structure of negation, okay? So negation in that case, so A implies bottom is simply defined as A star tensor bottom, okay? So you see, and this is the important point, this in logic, in classical logic, it means not A or bottom, okay? But in the logic of ribbons, the disjunction and the conjunction coincide, okay? So here it's written not A and bottom, okay? And this difference between the disjunction and the conjunction is the reason why we have a topology, okay? So anyway, there is a notion of negation here, and in fact, the functor which transports a proof into a tangle is faithful, okay? This is the main theorem. So that means that if we want to know when two proofs are equal in this logic, well, it coincides with topological equality of the ribbons, okay? So this means that, if you like, we can think of a proof and its equivalence class of equal proofs as such a tangle modulo deformation, okay? And the whole point is that when we build, I mean, this, if you like, subcategory or kind of subcategory coming from the proof theory is designed so that there is no knots. So there, I mean, there is no cycles. So a typical illustration is this. So this is a proof from 6 negations to 4 negations, okay? And it's organized like this. So there are some flows of negation in the proof, okay? And you can think of this proof as some kind of strategy. So where every functor may be seen as a move in a game. And here the strategy connects the moves, input moves to the output moves. So this thing here will be transported to a tangle which is called, so every time you have a negation, you add a little bottom here. So the tangle, what it will do is just, so here you should have 4 of them. It will just forget the dynamics of the proof, so the time, if you like, and just remember these connections. Okay. And so the difference between a proof and a knot is that a proof, whenever you have a link, there is an outside and an inside. So the outside is the world of the player, of the person who tries to prove the theorem, and the inside is the world of the refutator. Okay. And if you forget this information, then you are in a place where you can do these cycles. Okay. So in particular, if you want to think about general vector spaces or general modules over like quantum group, then you will have these flows between 2 canonical, I mean, constructions. So if you put tensors of negations of tensors of negations, you will have a full tree. So a typical example of this is this one. Okay. So this is a proof that double negation of A tensor double negation of B implies double negation of A tensor B. And you should think of it as a kind of if you like, a foam, okay? But here, because we are working with a very basic logic, we have trees becoming trees, okay? So, but you see this two negations, so R and L means the two negations. This comes from the fact that one negation is right adjoint to the other negation. So these two negations, they are transported, okay? So a proof really can be seen as a sequence of canonical transformations, okay? Transporting this tensor of double negation of A, double negation of B here, so this is the tree, in 3 steps, into double negation of A tensor B. The point is, if we look, it's exactly like in knot theory, if we look at the little generators, we don't see exactly the proof. The theorem that of, the faithful, I mean, the fact that the functor from proofs to knots is faithful says that, in fact, the proof here is completely described by the flow of negations, okay? So if I had braidings in my logic, then really the proof equality, or the notion of proof, is entirely described by these flows here, okay? So here, so how does it go? So you can think of it as the environment asking a question. This question is transported to the left, so the left component, so here, this negation. Then here, there is at some point an answer coming, so there is a little transport, and so this question here is transported to here. Now there is an answer, and the answer is transported here. This describes the proof entirely. And I should mention, okay, that this is the free structure of a lax notion of Frobenius algebra, okay? So in particular, the two negations here are correspond to the duality between a Frobenius algebra and its dual, okay? So 5 minutes, that's very generous. So maybe in 5 minutes I can show, okay. And again, the basic idea of this, if you like, is proof, this functor from proofs to knots is to transport the proof I've just shown you, okay, so it goes from double negation of A tensor double negation of B into double negation of A tensor B, to a tangle which goes from A tensor bottom, tensor B, tensor bottom into A tensor B, tensor bottom. And this tangle completely forgets the logic. It only remembers that this, if you like, this port is connected to this one. Then this one is connected to, this one is connected to this one. And this one is connected to this one, yes. So if you like, the proof is entirely described here by a numbering of the links. So it is 1, 2, 3, 4, 5, 6. And the proof is there, okay. Again, this has to do with the fact that the logic is very small, okay. But on this logic, we can kind of extract ourselves from the usual syntactic notation for proofs, okay. That's the idea. So let me explain briefly how I prove the theorem. So the idea is to construct the free dialog category. So it's two things at the same time. From one point of view, it can be seen as some notion of category and where the objects are games and the morphisms are so-called innocent strategies. But now I want to put some topology on the, on the links. So in a typical strategy, someone asks you a question, you will answer. But here maybe the link as a topological, as all the obstructions of topology. Okay, so when this link goes here and here. Okay. So in particular, something you can do is take negation of A and then have the negation turn around the formula. Okay, which is something we don't do usually in logic. But at the same time, if you want to follow the logical approach, and it's very useful here, in fact. Okay, that's the important point. It's very useful to look at the way people put logic usually. Well, then the objects are formulas and the morphisms are proofs. And the proof looks like this. so this is what I call ribbon logic, okay? Really, it's so the idea is that at every point of the construction of the proof, you have, it's really like a kind of multi-category or operatic thing. So you have a sequence of formulas and one formula on the right only, okay? And now, so you build such things, and just to show you, for instance, so it's really like cyclic operas, you see? If you have something that goes from gamma A into bottom, then you can transform it into something which goes from gamma into right negation, okay? And now if you have something which goes from gamma into bottom, you can transform it as something which goes from gamma into left negation. Okay, that's the difference between the two negations here, okay? And so now, okay, how do we do exchange? So the idea is that when we turn hypothesis in our logic, then in fact it boils down to having a little element of a group. So this group is the group essentially of some kind of ribbon version of braid group. So when you're kind of allowed to use the usual braidings, but also you can twist the links. And so for every element of the group, okay, there is an action on the set of on the numbers from 1 to n. So you use that action here to describe the change, change of ordering of the hypothesis. And so, well, the ribbon group can be presented. It's very easy. C commutes with A and B in 2 steps. Okay? And this is exactly the definition of a braided monoidal category. Okay? Because a braided monoidal category is more than a monoidal category with braiding. In fact, it's kind of multi-category with braiding. And this is where we see it. Okay? And so if you do that, then you can give some very precise notion of normal form, canonical form for your maps in your free dialog category. So there are proofs with a good shape. And from that, you can show that if you have 2 proofs with the same underlying topology, the same underlying tangle, very carefully you destroy the proof. And by induction on the depths, you show that they should be equal. Okay? So every topological equality, if you like, in the world of ribbons, lifts to an equality in the world of proofs. And so you get this theorem that the functor is faithful here. Okay? And I must say it's the kind of theorems we like because for the moment in all the proof system we had, we never were able to have a simple notation for equality. So typically there are always little problems. And here it works because we have an explicit negation. Okay? So for instance, if we start from a free, so if we forget the flow of negations, then we cannot have such a faithful, functor from proofs into a topological world. Okay, thank you.